Ah, perfecto. Bueno, hola, buenas tardes. Bienvenidos a nuestro coloquio extraordinario Arcadio Poveda. Empezaré hablando en español, pero la charla creo que va a ser en inglés. Bueno, hoy tenemos el honor de tener a María Alessandra Papa, que nos visita del Instituto Max Planck for Gravitational Physics en Hannover. Les voy a tratar de decir un poquito acerca de su trayectoria, aunque es bastante larga, entonces la voy a resumir lo más que pueda. ¿Ok? Bueno, la profesora Papa obtuvo su doctorado en 1997 en la Universidad de Roma. Después hizo varios postdocs. Estuvo en el MPI, que es el Max Planck también, por Gravitational Physics, en Golm. Después estuvo estuvo otra vez en Golm. Bueno, estuvo desde el 99 hasta el 2003, ¿ok? En Golm, haciendo su postdoc. Y actualmente y desde el 2007, es Senior Scientist del Max Planck Institute en Hannover. También es profesor de ondas gravitacionales en la Universidad de Leibniz, en Hannover también. Ella es líder del grupo de gravitación del MPI en Hannover, en donde hay 15 científicos que están trabajando en la detección de ondas gravitacionales, y fue parte del LIGO desde hace unos años, en donde recibió pues, varios premios. Les voy a decir algunos, que son muchos también. En el 2017 recibió el premio Bruno Rossi del American Astronomical Society, junto con LIGO. También obtuvo en el 2017 el premio Princesa de Asturias, también junto con LIGO. Y en el 2006 el Breakout Prize in Fundamental Physics. Ha recibido otros premios en el 2016, Gruber Cosmology Prize. En el 2014 recibió un premio en el American Physics Society, y ahora participa también también participa en el Council de la Unión Europea para evaluar todos los proyectos que se mandan y que se piden en el Council de la Unión Europea. Entonces, por favor, Alessandra, now we will change to the English. I think it's all. Okay.
Now it is.
Perfect.
All right. Well, thank you very much for the introduction, and thank you very much for the opportunity to talk here today. Perhaps this is a bit wishful thinking on my side, to be telling you about the next big gravitational wave discovery, but I hope that's in fact what we'll be talking about. Okay. Oh, I have to, exit because it tells me whether I agree to the recording, and it won't let me go further until I agree. But, okay. Apparently, good. I was able to. Yep. Yeah. All right. So, I'll be talking about gravitational waves. Gravitational waves are a direct prediction of Einstein's theory of general relativity, and they are deformations of space-time traveling at the speed of light. How were they produced? Well, by masses, distributions of masses that display a time-varying mass quadruple. Okay, so this is a sort of a primer. Imagine that there is a gravitational wave traveling in this direction from far away, and that there's these two rings of test masses. The effect of the gravitational waves, of the two polarizations of the gravitational wave, is to vary the distances of the masses in sort of these ways, all right? And this I'm showing you because I want to illustrate the principle of detection. How does one detect gravitational waves with ground-based interferometers? These are instruments that are now taking data, and these are the sort of instruments whose data I'll mostly be talking about. So it's very simple. Imagine a gravitational wave impinging on the plane of these two arms. The two arms represent laser beams, okay, shot in phase in two perpendicular directions. And if you remember what the gravitational wave does to the test masses, you can imagine that what it does to these two arms is that it contracts one, and it sort of pulls and squeezes them, right? Like the test masses. And so I've indicated here like this. So each arm sort of contracts and squeezes. And what happens is that this contraction and squeezing, varying so the arm length, produces an interference pattern that depends on it when the beams are recombined, okay? And so what one measures, basically, is this, through this interference pattern, is the extent of this squishing and extending. And it turns out that this is proportional to the gravitational wave amplitude. So if I had a stick, I would be pointing to that equation there that says that delta L, by how much the arms change their length, goes like the product of L times H. And so since that's the thing that you measure, you want to make it as big as possible. And so what you do is you try to build an instrument that has these arms as long as possible, okay? And these are the instruments that I'll be talking about, because these are currently the most sensitive instruments operating. They're the LIGO detectors, one situated in Hanford in Washington State in the US, and the other one, the other end of the country in Louisiana. That's the Livingston detector, about 1,900 kilometers apart. These detectors have been taking data since 2001, and then have undergone a major upgrade and starting taking data again in 2015. In a configuration that was operating, that was more sensitive. And this is why they're often referred to as the advanced LIGO detectors, so because they had been upgraded. And they underwent several observing runs, observing run 101, the second 02, 03, 04. And actually, right now, what's happening is 04, the second half of 04. And the first one was in 2015. And you can see here a measure of the sensitivity of the detectors. It's these distances in megaparsecs. And these represent the average reach. So how far can these detectors see certain reference systems, which is actually the coalescence of two neutron stars. So this is not so much to focus on the reach itself, the number, but just to see that they are still undergoing upgrades. So they haven't quite reached their final sensitivity. And we're now in the middle of the second half of 04. A sad note, the gravitational wave data is actually not released to the public until more than 2 years after it is taken. I was part of the LIGO scientific collaboration until 2018, and I worked very hard since its beginning in it, but then I decided I wanted to try encourage actually the data to be released earlier, and I also wanted to analyze the data with more freedom, not with 2,000 collaborators that I don't choose. So now I'm actually having to wait the 2 years. So this is, for me, is very sad. Anyways, the LIGO detectors underwent an upgrade, and in 2015, we were getting ready to start the observing run. And before each run, there is a period of time in which it's kind of a dress rehearsal. The detectors are basically in the configuration they will be during the run, the scientific run, but it's not really, doesn't have that tag yet. And it was during that week, before the official start of the run, that we saw the first ever gravitational wave signal. This is GW, gravitational wave 15, because it happened 2015 in September, the 14th of September. And what was seen was the coalescence and the merger of two black holes of about 30 solar masses, about. And so this is the signal, how it looked once you time shift the signals in the two detectors so that they align as if they arrived at the same time. Since the locations are different, they actually didn't quite arrive at the same time. And the gravitational waves are produced because there is a time varying mass quadrupole, as you can see. Okay, and if you haven't read the detection paper, I would advise you to do that. That's not the one, though, I cite here, because I think that paper is actually a very interesting one if you're not super familiar with the topic, because it shows you the basic physics in very, I want to say basic, but I would not like it to have that slightly derogatory. It's the fundamentals. It's the essence of why the signal, you can be convinced that these were actually two black holes of those masses coalescing. And this was one of the results, actually, of the paper. Not only was the first detection of gravitational waves, but it was direct observation of two black holes. Big results, big prize that came in 2017, awarded to the three fathers of LIGO up there, Barry Barish, Kip Thorne, and half of the prize to Ray Weiss. There was an announcement in Washington in February, and then a big party in Stockholm for some of us. All right, so since then, there have been more detections. Yeah, this is what I wanted. Lots more signals. And the ones detected by the gravitational wave detectors are the blue ones. And what am I showing here are just ordered in a way that's pretty. Every sort of vertical line has 3 dots. The 2 lower ones are the masses of the objects that coalesced, and the top mass, because the y-axis has solar masses, is the mass of the object that was produced. So each one of these is a coalescent signal of the merger of the 2 black holes that gave rise to the sort of top mass black hole. And so in 2003, which is the run that is completed, and for which actually a catalog is out, it was published last year in PRX, there's about 100 of these. But actually, I was at the APS meeting last month, and from the first half of 2004, the LIGO, Virgo, CAGR collaboration have now recorded basically just as many. So actually now the number of coalescences is about 200. Unfortunately, there's no plot that I could find. It hasn't been released yet. So what I would like to talk about, though, now is something completely different, because as interesting as observing coalescences is, and there's a whole now industry of people trying to extract information from these observations about, for example, the population of black holes that's out there, and what can we learn about how these were formed, okay? Or fundamental tests of GR, or even cosmology that can be done with all these detections. I want to talk about a different signal that's not yet being detected, and that would be a continuous gravitational wave signal. The sort of signals that are binary coalescences last, of the order seconds for neutron star mergers, but that first, for example, gravitational wave signal of 30 mass black holes lasted a fraction of a second. These are very short signals. I said would like to talk about signals that are always there. And you could ask, well, what is the varying mass quadrupole that can produce something like that? Well, imagine something like a neutron star, so something extremely compact that doesn't have a completely spherically symmetric shape, and it obviously spins. All right, this is basically like two masses spinning around each other, but it just, as long as that deformation, that ellipticity, that's what people call it, is sustained, the object will continue to emit a steady stream of gravitational waves at twice the rotation frequency, okay? And the ellipticity, so the measure of the perturbation, is described in terms of the ratio of the difference of the moment of inertia tensor. So it's like how it's the delta R over R, and R is the radius of the star, okay? So it's a measure. So first of all, you could ask, all right, suppose that we measure it. What's interesting about that? What could we learn? Well, we could learn perhaps something about what sources the ellipticity. And is there a possibility that this scenario could happen? Well, we know that neutron stars are created in messy environments. Collapses of supernovas. And these are very unlikely to be perfectly spherically symmetric. So it is not unlikely that some sort of deformation might be sort of there at birth. And there are people who study and make models of neutron stars in these rather complicated scenarios that think that these deformations might be sort of might persist as the neutron star cools and the crust of the neutron star solidifies quite for very long times. Other scenarios, we know that neutron stars are very likely to have starquakes. And there's indications of this in flares that are observed, giant flares from neutron stars. And more recently, even though people had sort of thought about that, we know that neutron stars glitch. And they've actually connected the glitch activity to perhaps okay, I didn't do anything. To possibly sort of readjustments in the crust. Yes, it's true that glitches are also, and the leading theory is that they're due to the unpinning of the neutron fluid vortices inside the neutron star, but on the other hand, a bimodal distribution of glitches, of glitch durations is observed, so perhaps there isn't just one cause of glitches. It could be, it could be an indication of starquakes. We have neutron stars in accreting systems. Accreting systems, the matter accretes funneled in hot spots, and that is a kind of a natural source of asymmetry, that hot spot. Variations of density, pressure, could be building of mountains around that. Then there's internal magnetic fields, and those could perhaps produce and source a sort of a deformation. Now, all of these scenarios relied on quantities that are very, very poorly known. And so people have tried to ask simpler questions, like what is the maximum ellipticity that a neutron star could sustain? This because if even the maximum ellipticity is so small that there's no chance of detection, well, we might as well focus our attention somewhere else. And unfortunately, even for a simple question like this, the ranges and the answers are scattered all over the place. And this is because it turns out that the simplest way to answer that question is to ask what is the maximum strain that the crust of the neutron star can sustain before it breaks. And that in turn seems to be, is connected, the way that it's modeled, is connected to the sort of the breaking strain, the sigma of the material. And that's, again, something that people come up with configurations such that that breaking strain can vary by orders of magnitude. So 10 to the minus 5 to about 10 to the minus 8, the maximum ellipticity, all right? The smallest ellipticity is a horribly low value, and that's what you get when you imagine that sourcing the ellipticity is just an internal magnetic field, and it's not even too strong, okay? So 10 to the minus 14. So we go from, let's say, 10 to the minus 3, 4 to 10 to the minus 14, 10 orders of magnitude. That's not, there's a lot of uncertainty. There has been a proposal based on observations. So about, that there might be a population of neutron stars that present a minimum ellipticity. And that was put forward by Owen et al. In 2018. And what they looked at was pulsars. Pulsars are neutron stars for which you can measure period and period derivatives. And this is what's plotted on this plot, period and period derivative of a set of pulsars for which, because you'll see there's the stars and the little blobs, the circles, well, really concentrate on the circles because this is the estimated intrinsic period and period derivative. In other words, what we observe might be affected by sort of proper motions of the object. Well, they've tried to concentrate on a sample of pulsars for which they were quite confident they could actually estimate the actual intrinsic frequency and frequency derivative, and those are the purple dots. And with them superimposed here, you have lines that correspond to populations of neutron stars that evolve evolve meaning the frequency and frequency derivative changes according to, because they are either emitting gravitational waves, and that's the orange line, and only gravitational wave emission is responsible for the loss of kinetic rotational energy. And the two orange lines represent an ellipticity sourcing that loss of that emission of gravitational waves for 10 to the minus 8 and 10 to the minus 9. And the other lines are ones where you have not only loss of energy due to gravitational wave emission, but also, and that's the more standard way in which it is thought that neutron stars and pulsars in particular lose energy, which is magnetic braking. And the different lines correspond to different magnetic field values, although assuming underlying an ellipticity of 10 to the minus 9. And so what this plot, when you look at it, kind of makes you wonder is, well, there seem to be no objects, or very few, right, with an ellipticity which is less than 10 to the minus 9. And so that this could actually be a sort of indication that that there's a population, that there's a population of pulsars only evolving due to gravitational wave emission with a minimum ellipticity of 10 to the minus 9. I actually personally think there could be other explanations, and since this is a sample of known pulsars, these objects, first of all, have to be seen electromagnetically. And so there could be other reasons that one doesn't see them, but they are there, and it's simply that they're not emitting for example, the radio emission is switched off because the magnetic field is too low. But anyways, I think it's interesting to note that. So 10 to the minus 9 in terms of ellipticity is an interesting value for this reason. Okay, what could we learn if we actually do observe gravitational waves that are continuous? Well, we could learn, first of all, about the ellipticity of the object. And hence, if we saw an ellipticity of 10 to the minus 5, well, this would tell us something about probably a pretty, or 10 to the minus 4, a somewhat more exotic equation of state than the standard ones. There are 100 million neutron stars or more in our galaxies. And currently, the sample of the ones that we know of is a few thousand. And so this probe, gravitational waves, could give us perhaps access to part of the population that's completely electromagnetically invisible. And then what? You have to think about continuous gravitational waves as the gravitational wave equivalent of pulsars. So in the same way that the sky, the light sky, is, there's transient astronomy, and then there's this whole branch of astronomy that's pulsar astronomy. Well, that is the corresponding in the gravitational wave sort of channel. And so with observations that can last tens of years, comes the potential for exquisite precision. And so tests of GR, for example, there's papers out about non-GR polarizations, but basically it's a completely different probe to test GR. If we could have an observation of a continuous gravitational wave in conjunction with EM timings, so knowing the spin frequency of the object, then we could understand what the emission mechanism is, because depending on the emission mechanism, the relationship between the gravitational wave frequency and the pulsar spin frequency is different. We could, for example, detect R modes, or we could see differential rotation in the star. Even more intriguing it would be if we find that the signal doesn't come from a neutron star after all, and there are I would say more speculative scenarios in which this could happen. So how strong are these signals? Well, these signals are very weak. They're orders of magnitude smaller than the binary signals that are detected nearly every day. And this is for a source emitted at 1 kilohertz at a distance of a kiloparsec. We're looking at amplitudes of about a few times 10 to the minus 25. And the binary in spirals that we're detecting are at the level of 10 to the minus 21. So how can we possibly hope to detect them? Well, we integrate the signal, okay? It's trivial if you have a very weak sinusoid. If you integrate for 10 seconds and you take an FFT and then compute the power, you basically don't see it. But if you integrate for 5 times as long, the signal adds coherently, the noise adds incoherently, and there comes the peak, and you can see it clearly. And so that's the basic idea. If you know where your source is, since the detectors, right, sit on the Earth, and the Earth spins around its axis and moves around the sun, so it moves with respect to your neutron star, your galactic neutron star, well, then the signal will appear Doppler modulated. So, okay, if this is not a big deal, if you know where your source is, you know the shape of that Doppler modulation, you can correct your data and basically take it out, and then you're back to conceptually the Fourier transform, okay? And the same for any intrinsic spin down that the source might have, okay? It doesn't need to be a sinusoid. If you know what the spin parameters are, you can correct for them and then detect it optimally over long periods of time. And so you can hope to observe it for months and months, and this can actually make it possible to observe it, even if the signal is very weak. Okay, so this is there's many lines and plots, but really what I want you to look at in this figure is simply the two axes, which one is spin period and period derivative. And this is the sample of a few thousand pulsars that are currently known. And what I stuck there on the bottom of the x-axis is the corresponding quadrupular emission gravitational wave frequency that's expected. So if any of these pulsars were emitting due to a mountain on it, this would be the frequency at which we would be observing it. So a frequency that goes from 0 hertz to 2000 hertz. Okay, but what about the detectors? Where are they sensitive? And this is as a function of frequency, the noise level in the detectors. And I don't want to go into more qualifications of what I mean by noise level, but you can understand that it's something that when it's low, it's better, because we will be able to detect signals that are weaker in the so-called range of high sensitivity of the detector that goes from about 20, 30 hertz to about 1 or 2 kilohertz at the most, okay? So that's the frequency range in which the detectors are sensitive, which is, if I go back here, you see a lot of the pulsar are actually below the 20 hertz line. Okay, so the subset of pulsars that we know of that are in the LIGO high sensitivity band, which is the high sensitivity band of all ground-based interferometers, are only a few hundred. Okay, with gravitational wave frequencies expected in this range, there's 1 dot per pulsar, and this is the frequency derivatives. So obviously, a good place to start if we want to detect a continuous gravitational wave signal is we know the frequency derivative, we know where the object is. We can just do targeted searches, and in fact, these are done routinely. And unfortunately, we've had no detections. There's been no detections. And so the name of the game is then upper limits. What's an upper limit? Since you haven't detected anything, but you do know what is the strength of the signal you could have confidently detected had it been there, you can definitely exclude that that pulsar is emitting at that level. And that's the upper limit level. It's the signal, it's the weakest signal that you can confidently exclude not being there because your search hasn't detected it. And so the upper limits are usually given in this form as a function of signal frequency. So a single pulsar would be 1 point here at the frequency expected from a pulsar spinning at the frequency of the object that you're targeting. You haven't detected anything, so based on the sensitivity of your search, you can say that the gravitational wave amplitude has got to be smaller than that value. Okay, so these are upper limits. Now, an important benchmark is the so-called spin-down upper limit. In other words, you get a number. Gravitational wave amplitude has got to be smaller than, let's say, 10 to the minus 26. All right, what does that mean? Well, a good thing to compare it with is, since you know for that pulsar how fast it's spinning down, you can ask yourself, well, assuming that all the spin down was due to the emission of gravitational waves, what amplitude would that correspond to? What is the amplitude that would sustain emission at the level that I see? Okay, well, that number depends only on the distance of the source that you know, the spin down frequency and the frequency of rotation, and the gravitational wave signal cannot be higher than that, obviously, because if it were higher, the spin down that you'd observe would be higher. Okay, and so this is actually a busy plot that shows the upper limits released for all the pulsars that were targeted in the last big survey for all known pulsars done by LIGO. And what it shows is the upper limit values as a function of frequency, as I explained below. And forget the pink curve for now. That's a sensitivity estimate that's there just to reassure the reader that the upper limits lie where we would expect them. And then each result is a star, okay? And that's the upper limit value. And for each result, so for each pulsar, what you have is the spin down limit, okay? So unfortunately, for most pulsars, there's, as I said, about 200, the upper limits that we can place are actually above the spin down limit. So they're not very informative, in other words. You're basically saying, I know that the pulsar doesn't emit more than X, but actually, just based on the spin down limit, you know that the maximum signal has got to be lower than a number that's lower than X. So your observation is really not informative. But for a few, and these are the ones that are circled, you see, some stars are in circles. Those are the stars for which actually the spin down limit was beaten. And in particular, for the Crab pulsar, it was beaten by factors that are quite significant, more than 50, okay? But still no detections. So this plot, the takeaway message is for most pulsars, known pulsars, the upper limits, now look, are below 10 to the minus 26. So that's the sensitivity of the searches. Okay, this is what integrating for a year actually brings you when you know the source position. But unfortunately, the inferred spin down limit is even lower, apart for about between 5 and 10 of them. Okay, now recall that the gravitational wave amplitude is connected to the deformation of the object. So if you know the distance and the gravitational wave frequency, for every value of the upper limit on the amplitude, you can actually say something about the upper limit on the ellipticity. And so this is just the same results as before, but shown now as a function of frequency again, in terms of the upper limit on the ellipticity. So for every pulsar, you say the ellipticity has got to be lower than the upper limit value. And what I want to say with this plot is that you see the pulsars for which the upper limit was beaten, okay, which are the ones sort of, unfortunately, they're all in the top left side of the plot. So they're the ones for which actually the spin down limit is very high, corresponds to ellipticities that are very, very high. I showed you some estimates of what could be the maximum ellipticity of a neutron star. And it was, between 10 to the minus 5, 10 to the minus 8, and 10 to the minus 3 for really crazy, cuckoo, exotic equations of state. And unfortunately, the spin down limit for those objects for which we beat the spin down limit is really very high. And so, unfortunately, that's why I'm not so super excited about searches for non-pulsars. There's perhaps one exception, which is that pulsar there at a few hundred hertz. You see there is a little isolated result encapsulated, which means it's actually beating the spin down limit, but not very much. So that's the status for the first thing that one could do, target known objects. I think much more interesting are accreting systems. Because, as I was saying before, there is a natural way to actually have an ellipticity. And in fact, it has been noted since quite a long time, but again, this is a paper by Patruno and collaborators for 2017 that shows the distribution of frequency, spin frequencies, for accreting neutron stars. And if you stare at it for long, you might think that's sort of bimodal, but you don't need to stare at it for too long to see that there is a brisk cutoff. We don't observe accreting neutron stars spinning much above about 650 hertz, okay? And that's not at all anywhere close to the breakup frequency of a neutron star that's more in the over 1,000 hertz. So why is that? why don't we, isolated pulsars, we do see spinning a bit higher, but these, they don't. So the idea that was put forward, again, it's not a new idea, is that there's something that's balancing the accretion torque, okay? Such that, because you'd expect the spin frequency of these objects that are accreting to increase. But we don't see this very high frequency, and so perhaps there's something that's balancing the accretion torque. What could that be? It could be gravitational wave emission. And one of the reasons that it could particularly be gravitational wave emission is because that is, you're looking for something that kicks in quite effectively and quickly and does produce that kind of clean cut without so many tails. And that's what the gravitational wave balancing mechanism would do. And in fact, there's people who even recently sort of simulated different accreting systems, and they could only reproduce the distribution that's observed if there was gravitational wave emission of some sort. Okay, so it seems here that we have some observational hint that actually gravitational waves might be playing a role. So this is why I think this is interesting. So one does the search, and there is an important quantity. You can calculate the torque balance. So what is the amplitude that would produce, what is the gravitational wave amplitude that would actually balance the accretion? And so you find the mass of the neutron star, the torque arm, you can imagine that should be there, and the X-ray flux. And the reason why the X-ray flux is there, it's that it's the quantity that we use to sort of estimate the mass accretion rate that is important to estimate the accretion torque. And so basically, you can say if gravitational wave emission happened at that frequency, this is the amplitude of the gravitational wave emission that we need for torque balance. So searches are done. Unfortunately, spoiler alert, I'm not going to tell you about any detection. So searches are done, there's no detection. And it's interesting to see, though, how far are these upper limits from the torque balance upper limit. And there again, here is a function of frequency, the upper limit. Now, a function of frequency for the brightest X-ray source in the sky. Why is that interesting? Because that's the source that we'd expect to have to need the highest gravitational wave emission to balance the torque. Okay, so this is Scorpius X1, and we don't observe pulsation, so we don't know at what frequency this source is emitting. So this is now a search that's significantly more challenging to do, because we got to search a whole bunch of frequencies and spin down values. And by doing this, we lose some sensitivity. So you see we're at best at upper limits of 10 to the minus 25 and just about hitting the torque balance, okay? So I think this is very promising. And this, I must say, it's also the torque balance, assuming somewhat pessimistic, making some pessimistic assumptions, because the torque, how strong it is, depends on where you apply it. And this is a torque applied at the neutron star radius. If the torque was applied at the magnetosphere radius a bit further from the star, then the torque would be higher and their upper limits would already be lower than that. So this is a very conservative plot. And we are at about 6 times 10 to the minus 26. So worse than the known objects. Okay, so what I find very interesting personally, and this is what I spend a lot of time doing, is what about the neutron stars that we do not see? So not the Scorpius X1s or the known pulsars, but what about one of the objects that's out there in the sky, possibly, close enough and bumpy enough, but not emitting a pulse of radio or gamma or X-ray emission that's beamed towards us, and so we don't see it. So I don't know, though, where the source is. So the way one does the search is basically we assume a source position, spin, and spin derivative, do the phase correction, compute the power, and then move on to the next set of source parameters, okay? And the problem with that is that if you want to integrate over, several months of data in order to achieve the highest sensitivity, you find that you can resolve so finely the different values of the frequencies and sky position that you'd have to do this like 10 to the 28 times. That's, a number of times that absolutely you don't have the computational power for. And so this is the reason why for this type of search, optimal search techniques, which means coherently combining the data over the entire observation time, you simply cannot do. And so what one does is, well, you chop your data up in chunks, and you do your coherent search over the smaller chunks, and then combine the results. So these are the so-called semi-coherent searches. And you start with chunks, since you have at first to survey the whole sky and the whole frequency and spin down range. You start with chunks such that this is doable because you've got a very large parameter space. And you only concentrate your attention on the points, on the parameter space points, on those results that appear interesting. And on those, then, you kind of zoom in with another semi-coherent search that's a bit more sensitive because you made the coherence time a bit longer. And for that, you only keep the subset that's interesting. And on those, you do an even more sensitive search. The idea is that as you zoom in, you basically invest your computational budget on a smaller and smaller region of parameter space that allows you to do a more and more sensitive search and discard the points that were just noise fluctuations because they will manifest their non-signal origin when looked at on longer sort of time scale. This requires still a lot of computing. And so we use the Einstein at Home Volunteer Distributed Computing Project, and please sign up. It's a project that uses the idle time of your computer to do searches for gravitational waves and also for pulsars, for pulsars. And you can choose whether you want to help me look for continuous waves or look for pulsars in electromagnetic data. And then all the follow-ups are done on this very large supercomputing cluster in Hanover. So these are very, very computationally intensive searches. What I mean is that an all-sky search, like the one I'm going to show you the results of, done on O3 data, took 8 months of computing on Einstein at Home, 24/7. Okay, and that was just the first stage. And then a few other months for the post-processing follow-up. And this is what comes out, a paper. Unfortunately, again, we haven't detected anything. But we did set the most constraining gravitational wave amplitude upper limits to date, including beating the ones set by the LIGO scientific collaborations. This is the result, again, as a function of signal frequency, putative signal. If we had a source at this frequency, what is the maximum amplitude that we can exclude? That's on the y-axis. And the results of the Einstein at Home search are the ones in red. And the ones in black are the ones from the LV k on the same data. And what you find in orange are the so-called hardware injections. There are signals, fake continuous signals that the LIGO instrument scientists simulate in the detector, and they're sort of control signals. And it's very good because it allows us to really benchmark, and anybody who runs these types of searches, if you say that your upper limit is at a certain level, well, you should detect 90% of the signal, because it's a 90% confidence upper limit, at that level. And we do very well. In fact, we detect also ones that are below those injection 0 and 2, because they actually happen to have favorable orientations. And on average, I would say we're definitely doing better than any other search in detecting these. And you see, though, the upper limits, we're now at 9 times 10 to the minus 26. So the larger the parameter space, the more sensitivity we lose. Okay? And this is because we couldn't do the fully coherent search from stage 0. Okay, I'm getting close to concluding. Fine, but what are the chances of making a detection? Because I talked about the maximum ellipticity, but there's a complicated interplay between the ellipticity that you know an object with, how old it is, because that ellipticity does affect, for example, the frequency evolution. So if it's very old, it might just have spun down outside of the band, okay? And whenever I've asked that question, I mean, the interest of people doing continuous wave searches is rather specific. So we've simulated a synthetic, several synthetic populations of neutron stars and evolve them in frequency to see, what would the distribution of the parameters that we're interested in, the amplitude, the frequency, be at current time. And we've evolved them in frequency with a magnetic field and with an ellipticity. And so the interesting parameter, we considered various models, and interesting parameter was the birth frequency, the age of the object, the distribution of magnetic fields and ellipticities. This could well all fill a talk, so don't be surprised if you're not really quite understanding what I'm saying. The gist of the message is that we've considered various populations, varying the parameters in ways that's reasonable. And for the current population of detectors, basically, when you go and look at the expected number of detectable signals, you can see that for some models, you've got less than a % chance of detecting anything. And even in the absolute best cases, you could expect perhaps to detect a few, but with a very large standard deviation. So it's not surprising that we haven't detected anything. The situation looks a lot better for the upcoming generation of gravitational wave detectors, where we certainly expect a few with Cosmic Explorer, and even a few hundred, which means that if we don't see them, we'll at least be able to exclude certain distributions of parameters of the underlying population of objects. And I am not going to talk about objects in binaries, but I will say that if you look for neutron stars in binaries, which are very important because especially at the high frequencies that are sitting in the LIGO band, these there's most objects, most neutron stars are in fact in binaries. You are faced with having to expand the parameter space of search parameters even more to include the orbital parameters. And so this is just to say that this is a search where we really need new ideas. So young people here, if you want to get involved, there's lots to do. Need for new and clever methods to do this, because these searches are the way that they're being done now, they're not very sensitive. So, summarizing, the first detection of a continuous wave will open the field of gravitational wave pulsar astronomy. We are probing interesting source parameter ranges and very reasonable emission levels. Broad surveys are hard, and this is certainly a high-risk, high-gain enterprise. I can't guarantee that we'll have a detection with the current generation of detectors, but remember the history of gravitational waves. LIGO started and went through the first generation of detectors that was necessary to get that first detection and then the slew of other observations, and it was controversial. People didn't think it was, since there was no guarantee that this was a good investment. And the payoff when it comes is so exciting that it's worth the risk. This is what I think for continuous wave, and I think that the only guarantee for failure is if we don't try. And with that, I'll close here. Thank you.
Thank you very much. Thank you very much for your very nice talk. We have time for a couple of questions. Here we have one question.
Hello.
Hi.
Hello, thank you very much. I assume you can include constraints on the equation of state into constraining your parameter space, I would say. You can't? Not even with the ellipticity, or?
No. So what happens is that, as I showed, when you even consider different equations of state, these simply translate into a broad range of ellipticities, okay? And it's the other way around. It's hopefully our observations. If we observed a very loud signal, this would tell us that the equation, that the matter inside the neutron star would have to be pretty exotic. But if I measure, the moment I measure a signal, perhaps I can say something, but I can't use, all kind of normal equations of space basically give you ellipticities that vary in that range between 10 to the minus 6 and 10 to the minus 8. That we are starting to probe, but with a lot of degeneracy too.
Okay, thank you.
Thank you very much. In Zoom, someone wants to ask something? Here we have another question.
I'm asking a very stupid question. It's almost embarrassing.
No.
But if you have so many neutron stars that you're expecting that they are all sending a continuous signal, how can you select what you are observing? Mm-hmm. Because it's going to be noise everywhere, mm-hmm. that it's adding, and it's continuous noise that is adding up. So how can you mm-hmm. select something from that noise?
Okay. So first of all, of the many neutron stars that there are in the galaxy, at least if we take the subsample that we see as pulsars, of 2,000 plus, we have in the band of the instruments only about 10%. So first of all, in the band of the instruments, there's fewer. But more to your question, even if they were all emitting in the band of the instruments, this wouldn't be a problem, because we have a very fine ability to discern different signals. And so they're not overlapping for us in practice, right? This is the good and the bad. Make sense?
Okay, thank you very much.
So we can actually distinguish the frequency with precisions, which is at the microhertz level. Okay, microhertz level, and exquisite arcsecond precision localization. So these objects emit signals that we can distinguish very well. They're not overlapping.
So they're continuous in time, but not in frequency.
That's right, because they're single objects. So they, and yes, our ability to discern them makes them.
Thank you very much. Last chance in Zoom. Students. Well, I have one question. It's related to the estimation for the strain amplitude. In the formula you added in your slides, there is a, well, you say that the estimation is for 1 kiloparsecs. How realistic is this distance? Because maybe it's too close for us, or we cannot detect signal far away from 1 kiloparsec.
No, oops, sorry, which one? Sorry about that. It was, okay, there, yeah? Yeah, so the galactic center is at about 8 kiloparsecs. We know that there's, 10 to the 8, 10 to the 9 neutron stars in the galaxy. We expect the nearest neutron star, you can do the math, to be at about 12 parsecs. Now, the question is, it has to be spinning in the right frequency range. And then still, though, be strong enough to be detectable, meaning having an ellipticity that's high enough. And this is where that dependency that makes things not so trivial came in, and why we did the population. But no, 1 kiloparsec, there expect to be plenty of stars. And we know from the ATNF catalog that there are. I mean, there's tons of stars at a few tens and hundreds of parsecs.
Okay, thank you very much. If there is no more question, let's thanks again to Alessandra.
Thank you. Great. Well, I have questions for you, actually.